So, welcome student to the next class of Introduction to Nonlinear Optics and its application. So, in the previous class we have started a very important concept which is called the phase matching. Two different kind of phase matching we discuss. One is the phase matching due to this called birefringence phase matching, and another phase matching was the quasi phase matching. So, today we will extend our study. So, birefringence phase matching condition we will learn in detail, and in birefringence phase matching there are two types of phase matchings are there, type 1 and type 2. We are also going to learn what is this type 1 and type 2 phase matching. Okay. So, this is the structure of birefringence phase matching and quasi phase matching. This is the old picture, but it is a very important one. One should understand what is the birefringence phase matching. In birefringence phase matching, what happened? That the crystal should have two different kind of wave. One is ordinary wave and another is extraordinary wave. For uniaxial crystal, we have this kind of properties, and this NO and NE basically representing the refractive index of ordinary and extraordinary wave. So, NE is a refractive index, and this refractive index is a function of theta. So, now if I plot the index diagram, then we can see that there is a specific point as shown here, this point at which we have the phase matching. That means, any of 2 omega at that particular angle theta is matching of NO of omega, that is eventually our phase matching condition. So, that means, if I launch a light in that particular direction, the phase matching condition can be achieved. Well, so also in the previous class we find that the refractive index can be function of omega, and as shown here in the picture, that it is changing with respect to omega, and when it is changing with respect to omega, there is no way that we can have a phase matching. So, due to the dispersion, we never have n to omega is equal to n omega. So, what is the then what should we do? So, this is a very important picture of birefringent crystal, where we plot n omega and n 2 omega for ordinary and extraordinary wave. So, this is n omega of ordinary wave, and this one, the blue one, is n e, that means refractive index of extraordinary wave, and this is launched for 2 omega. So, when this is both are the function of omegas, but at this point the value is this, at this point the value is this. So, what happened that you can, if I make a horizontal line, you can see that at 2 omega point, whatever the value we have, at omega point I will have the same value for ordinary refractive index. So, ordinary refractive index at omega frequency having the same value, extraordinary refractive index at 2 omega frequency. So, this can be more clearly understood in this index figure. When I plot this index figure, when I draw this index figure, this is the optic axis, and we know that in optic axis, the direction of the optic axis, the refractive index of ordinary and extraordinary wave are same. That is why these things are touching here and here. Ordinary refractive index will never change, and it will not be a function of theta. So, it will give us a circle, but extraordinary wave can change with theta. So, we have elliptical structure. So, we have an ellipse in 2 dimension. These things we have discussed in our very previous classes, where we study the basic linear optics, but here you can see a point where they are crossing. This is the crossing point between the ordinary and extraordinary refractive index, and this crossing point is basically the point where two values are same. So, there is a possibility that we will have the phase matching at that particular point. So, that is the idea of birefringent phase matching. We use some crystal to generate second harmonic, where the phase matching condition can be satisfied through this NE and NO, this refractive index, using these two refractive index. Well, now the next thing is to calculate what is the value of this angle. We are talking about that there is a matching of refractive index, but this matching will be in particular angle. So, if k is a launched wave, k is the direction of the wave, then it is making an angle theta for which we have the phase matching, or for which we have the matching of the refractive index here over this. So, now we have this in my hand, that n o of omega is equal to n e of 2 omega at theta point. Now, we have the equation in our hand, that this equation is a very old equation. So, 1 of n e square 2 omega at theta, I want to find out the theta dependency. So, if I want to find out the theta dependency, in the right hand side cos theta and sin theta term is there. So, it is cos square theta sin square theta and n e 2 omega and n e 2 omega n o 2 omega square. So, now if I put these things here, the condition here, so what happened, that n o in the left hand side I put n e of 2 omega, just remove this omega and I put just n o of omega square, and in the right hand side I just replace this cos to sin term, so that everything become in sin. Our goal here is to find out the theta angle for which I can get this angle. So, when I replace this cos to sin, then we have 1 minus sin square theta, this sin is already there, this quantity we know, this quantity we know, this angle I want to find out, but my phase matching condition suggests that this is equal to NO. So, I just replace NO. Once I have this form, then the next thing is easy, we just replace this. So, the next step is to simplify. So, 1 minus NO square 2 omega, I will put it here, and then I just write minus of sin square theta NO square 2 omega here. So, these two terms are function of sin theta, and we have another two terms. I put this term in the left hand side and I am getting 1 divided by NO square omega minus 1 divided by NO square 2 omega. So, this is the ordinary refractive index. So, this is the ordinary refractive index of 2 omega and ordinary refractive index of omega, and in the right hand side we have sin theta. If I take sin theta common, then we have 1 divided by NE 2 omega and 1 divided by NO 2 omega. So, NE 2 omega and NO 2 omega, again these are the values. In this particular diagram, if I want to find out which value I am talking about, you can readily understand that which values are this. So, if I say N0 or NO 2 omega, NO omega, that means I am talking about the radius of this quantity. So, radius is NO of 2 omega, NO of omega, NO of 2 omega is the radius of this blue line. So, this radius is basically the value of NO omega, this radius, amount of this radius is basically the value of this quantity. NE of 2 omega is which value? At this point and at this point these values are different. So, I am basically talking about this amount, this is basically NE of 2 omega, and this amount from here to here is basically NE of omega. So, all these values one can find out with this index structure. Mind it is a function of lambda. So, omega is a fixed value here, for different omega we will have different structures. But the important thing is that if these values are provided, then we can readily find out the angle at which we have this condition valid. That means, this condition where in omega, n O of omega is equal to n E of 2 omega with theta angle. So, this angle is very important. So, we find the direction at which the phase matching condition is valid. So, in order to find this direction, these are my expression. So, once we have this expression in my hand, then readily I can calculate the angle at which the phase matching condition is there. That means, maximum efficiency of generating second harmonic will be achieved at that particular direction. So, that means, inside the crystal, if I launch a fundamental wave, then the launching angle is a very important criteria. I can't launch in any arbitrary direction, but I need to launch a very specific direction for which, compared to optic axis, I launch to a certain angle, so that my phase matching condition is valid, and once the phase matching condition is valid, we will have more efficient second harmonic generation. So, this is the process to find out this angle. So, if I know all the values of ordinary and extraordinary refractive index, then we can readily find out what should be my angle. Okay. So, this there is a cutting point, as I mentioned, at angle. So, this is called basically the critical phase matching. Once we have this angle, at this point they are matching. So, k is in this direction, and when the k is in this direction, so the s has to be in different direction, because s should be perpendicular to, if I draw a perpendicular line here in the surface, then s has to be perpendicular to that. So, there is a angle difference between k and s. We know that this is called the Markov angle. So, k and s will not be in the same direction for critical phase matching condition. And in critical phase matching, what happened? We have a matching of n omega and n 2 omega, any of 2 omega, but with finite angle. Now, there is a possibility that this angle can increase up to pi by 2, and then the figure will be something where this cutting point merges to one single point. There are 4 different directions, by the way. These 2 are other directions also where the cutting is possible, but here we can see that if I increase this n 2 omega, then there is a possibility that they are cutting exactly over x axis, because this is the x axis and this is my z axis or optic axis. So, along this direction, what happened, k and s will be parallel to each other. So, non-critical phase matching is a very important thing, where we have the additional property that k and s both are parallel to each other. And if I deviate slightly, then there is no problem, because they are parallel to each other. So, that is why it is called non-critical phase matching. So, criticality is somehow less in this particular case, where the phase matching angle theta m for here, as we mentioned, is pi by 2. So, when theta m is pi by 2, we have certain angle, certain direction where the phase matching is possible, and this direction is nothing but along x direction. So, this is a very important kind of phase matching, and normally by changing the temperature, there are a few crystals. If we change the temperature of the crystal, what happened? The refractive index, extraordinary refractive index may change, and when the extraordinary refractive index change, there is a possibility that it will reach to that value by not changing the ordinary, or by adjusting the temperature, it is possible to make this angle pi by 2. So, from critical phase matching, so we can go directly to the non-critical phase matching domain, and non-critical phase matching is much superior than the critical phase matching. Okay, now the next thing is type 1 and type 2 phase matching. So far we are dealing with the phase matching for which we are generating. So, what was the phase matching? So, let us write these things clearly. So, in type 1 phase matching, two systems can be possible as shown. For negative crystal, what happened that one ordinary ray and one ordinary ray can generate one extraordinary ray. Phase matching condition should be NO of omega is equal to NE of 2 omega. So, NO of omega means ordinary waves at fundamental frequencies. This is ordinary wave and fundamental frequencies, they are generating extraordinary waves. So, extraordinary waves are generating because of the combination of two ordinary waves, because this phase matching condition this is the process. So, let me write in terms of k, I think that will be easier to understand. So, k of ordinary wave with frequency omega plus k of ordinary wave with frequency omega can generate k of extraordinary wave with frequency 2 omega, 2 of k of ordinary wave frequency 2 omega. Now, if this is the structure in terms of k, then what happened, I can say here as it written that two ordinary wave of omega of frequency, two ordinary wave or O wave of frequency omega creates an extraordinary wave of frequency 2 omega. So, in k domain or for k, this is the expression. So, now if I write, it is 2 k ordinary omega is equal to 2 of no, it is just k 0. So, let me write it once again. So, here okay, I will do that later. So, two ordinary wave of omega merge to generate one extraordinary wave, this is one structure. Another structure is still possible, where we have in positive crystal we have a structure where two extraordinary wave of omega can create an ordinary of 2 omega. In the previous case, we have a structure like this, but another structure is still possible, we will show, where we can have this kind of thing. So, the drawing is not proper. So, maybe we can have this figure in the next slide. Yeah. So, this positive crystal, what happened? In the positive crystal, we have the velocity of ordinary wave is greater than velocity of extraordinary wave. That means, the refractive index of extraordinary wave is greater than refractive index of ordinary wave, and in negative crystal the opposite happened. So, this is the direction of k both the cases, and this is negative and positive crystal. This is the old slide I am using, because we have already learned this. To recapture what is going on, we show that. So, now we like to understand what is happening the OO system. That is exactly the thing I was trying to do just few minutes ago. So, let me do that once again, that two ordinary waves. So, here again let me write. So, OO system, what happened, that two ordinary waves are generating one extraordinary wave. So, that means 2 of k 1 0, here k 1 means ordinary and k 2 is extraordinary, written as O and omega, O and E, and here the frequency is 2 omega and omega for k 1. So, that is why I write it is k 1 and k 2 here. So, if I use this expression and then if I convert it to in terms of refractive index. So, k 1 is omega divided by c n of omega, n of ordinary wave with omega frequency. Here also k, so just we use this k is equal to omega divided by c, k of omega is omega divided c n of omega. We just use this expression both the cases. One case we use extraordinary refractive index NE because my k vector is extraordinary. K vector for ordinary we just replace n of O, and when I do these two things together we have the expression where we can see that ordinary refractive index of frequency omega is matching with extraordinary refractive index of frequency 2 omega. So, exactly this is the figure that we are looking for. So, for this kind of phase matching theta m one can easily figure out, and that is the value of theta m. Also we have derived this value, and this is happening for this kind of crystal where NO is greater than NE. So, what happened for OO for E system we understood. The next thing is that what happened for other scheme, that means what happened for EE to O system. EE to O system, what happened, two k1 vector with extraordinary wave. So, k e at omega plus k e of omega, these two extraordinary wave vector will be equal to k o of 2 omega. K of omega is represented by k1, k of E at omega represented by k1, and k of 2 omega is represented by k2. This ordinary and extraordinary are symbol like this way. Now, again we are doing the same thing, but here we find one important condition, that now instead of N e equal to N e of omega is now equal to N o of 2 omega. So, if I now try to find out the picture, then obviously N e of omega has to be greater than N o of 2 omega. So, this is a crystal where this is possible at this point as shown here. Now, one can again find out the theta m value. So, I can find out what is my theta, but there is a difference, there is a small difference between this expression and the previous expression. You have to be very careful. The previous expression we have already calculated. In the similar way, if you calculate, you can have a result something like this. So, this is a result for which we are getting second harmonic, but the type of the second harmonic is, it is the first type of, but this is a system where two extraordinary wave is generating one ordinary wave. In the previous case, we find two ordinary wave is generating one extraordinary wave. In this case, we find two extraordinary wave is generating one ordinary wave. So, go back to this expression once again. So, here it is NO to the power minus 2 omega, NO to the power minus 2 omega, and then in the denominator we have NE and NO. What happened in this case? It is NO, 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 NE, NO, 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 NE, but if you look carefully, here we have omega. In the previous case, here we have omega, in the later case we have 2 omega. So, there are two systems. Please note that this is OOOE system, and in this particular system I have refractive index of ordinary wave here, but the frequency at omega, and here we have refractive index of ordinary wave, but frequency 2 omega. Other terms looks quite same, but in this case 2 omega, 2 omega, 2 omega, but here omega, omega, omega. So, I suggest you to please calculate these things by your own way. This is the calculation that we have already done. In this calculation we have already done. So, that means this calculation. So, let me go back to the previous slide, so that you can understand. Yeah, here you can see the calculation for the crystal where two ordinary waves are merging to generate one extraordinary wave. So, this calculation is already done. So, here we can see that it is sin squared theta if I now write in terms of, so NO of minus 2 omega. So, please note that 1 by NO square is just represented as NO of minus 2 to just reduce the complexity of the this expressions. So, here we have 2 omega, this is my outcome that we derived here. Both the cases we have a negative sign, negative sign. So, this is the way we have calculated, and in order to calculate, one important expression that we have used is N of E of 2 omega theta is equal to N of O of omega. So, exactly the similar treatment you need to follow in the next case, in this case, but you need to careful about that, you need to use this expression, that now my condition is slightly changed, that any of omega of theta is equal to NO of 2 omega. So, I can put it as homework or the class work, and I want you, it will be very very easy calculation. So, I want the student to please do this calculation and match whatever the expression is shown here is the same thing that you are getting or not. So, with that note, let me conclude here. In the next class again we will start from this level and try to understand more about the phase matching condition, and the crystal symmetry is also be covered in the next class. So, with that note, let me conclude. Thank you very much for your attention and see you in the next class.